Hello and welcome to KNN. I'm Paige Sherrick.
I'm Evan McLeod.
And today's topic is aviation fuel.
Hello? Dear God, we just ran out of jet fuel.
Oh no. Well, fortunately, Team 2 is investigating an alternative fuel, ammonia. But it's not as simple as just pouring it into an engine. For more on that, we'll turn to Evan.
Thanks, Paige.
Commercial aviation still runs mostly on carbon-based fuel, and the industry is pushing toward net zero carbon emission by 2050. That is part of why our team is involved with NASA's ULI ALFA project, a 5-year, $10 million effort led at UCF by Dr. Jay Kapat to study zero-emission aviation. Ammonia is interesting because it is basically a carrier of liquid hydrogen. Hydrogen is a very attractive fuel source because, unlike traditional jet fuel, it contains no carbon. That means when it burns, the main product is water vapor instead of carbon dioxide. So why not just burn hydrogen? Well, here's the weird part. By volume, ammonia actually carries about 45% more hydrogen than liquid hydrogen. On top of that, ammonia is already produced and transported at a huge scale, with about 70% of it going into fertilizer. The catch is that ammonia is difficult to burn directly in a gas turbine because it has low flame speed, narrow flammability limits, and a high ignition temperature. So our project matters because if you can crack ammonia into a hydrogen-rich fuel stream first, you may have a more practical path toward cleaner aviation.
You know, he seems like a handsome and smart guy. Doesn't he seem like a handsome and smart guy?
You know, that is one way to describe him, Evan.
So ammonia looks promising, but it needs processing before an engine can actually use it. That brings us to the concept itself. Trevor, what's the big picture idea behind our system?
Well, you see, Evan, the catalytic cracking unit's primary goal is to decompose pure vapor ammonia into a mixture of hydrogen, nitrogen, and some remaining ammonia. As mentioned, ammonia itself is not a great fuel, but since it carries hydrogen, we can break it apart, aka crack it, and turn it into something that's usable in an engine. I have here a simple mock-up for what the full-scale design would look like on an actual engine. A relatively thin chemical reactor is wrapped around the nozzle of the engine. Ammonia cracking is an endothermic chemical reaction, so we need to add heat to facilitate the cracking. So we make use of the heat that is normally wasted at the end of the engine. This heat is conducted through the walls of the reactor and is distributed evenly with the use of a corrugated sheet insert, and also in part by the inherent thin plate design. Inside the reactor is a packed bed of catalyst material. In addition to the heat, the ruthenium boron catalyst provides active sites for the ammonia to carry out its reaction to higher efficiencies, upwards of 70% cracking in ideal conditions. So to recap, we take ammonia, add heat, and give it a catalyst, and the result is a carbon-free fuel that can be integrated onto existing aircraft engines without a complete redesign of the engine. Thanks. Back to you, Evan.
Okay, so that was the vision. But for senior design, we need something we can actually build, test, and learn from. Paige, what did we actually make?
Due to limited access to an engine, the team pivoted to do a lab-scale setup. This design maintains key features from the full-scale system, including conductive heating through the bottom of the reactor, which simulates the hot walls of the LEAP-1B engine. Because everyone's so eager to learn about the lab-scale reactor, I'll do a brief component breakdown. Each component is uniquely incorporated and has gone through multiple rounds of iterative design to get to where we're at today. One of the biggest problems with a circular reactor is that there are cold spots, which is why this was designed with thin rectangular walls as well as a corrugated sheet to enhance uniform heating. The rectangular body will support the collar flange assembly. Additionally, there are MPT ports as well as a graphite gasket, which provides for leak-tight sealing. Lastly, a corrugated sheet is incorporated into the reactor to enhance heating by conductive heat from the base of the reactor upwards, promoting uniform catalyst heating. All these components are carefully manufactured in the machine shop before a synthesized ruthenium catalyst is placed within the reactor to get ready for testing. Wowee, what a smart and handsome girl, right, Evan?
Sure.
Anyways, the project just wasn't an idea on paper, it turned into a real prototype.
But the real question is whether it actually worked. Vittorio, how did you test it, and what were you looking for?
I am here at the chemical lab where the ammonia magic happens. Here we have the bench flow system in Dr. Blair's laboratory, that was used to heat the catalytic cracking unit and control the inflow properties. The ammonia was supplied through this gas canister, and the heating is thanks to a row of radiating heaters below the reactor. As for the input conditions, there are various controllers for the purposes of managing the environmental properties of the ammonia flowing in. The reactor itself, which is now on display at the Smithsonian Museum, had pressure transducers and thermocouples for measuring the physical ammonia properties across the reactor. The hydrogen and nitrogen output is then separated in this gas chromatograph and further measured for composition properties. Their measurements of success was a targeted conversion of 50% and a very minor temperature and pressure variation, with, of course, safe operation above all.
Very interesting. Also, I'm being told that this project involved a lot of heat, pressure, and engineering.
Locke, what changes were made to the project, and how did feedback shape the final plan?
Yeah, so at this point, the design we have is actually pretty different from where we started. Originally, we were working with a coated catalyst on a monolithic reactor where the reaction happens along the walls to maximize the surface area. But once we moved to a packed catalyst approach, basically filling the reactor with catalyst instead of coating the walls, that geometry didn't make sense anymore. From there, what became clear, especially after feedback from our advisors, was that heat transfer was going to be one of our main focuses. So we looked into adding internal pins to move through the reactor. But once we brought that idea to the machine shop, it was pretty clear that that would be difficult and time-consuming to manufacture. So that pushed us towards a corrugated sheet design, which still improves heat transfer but is much more practical to have manufactured externally. The testing plan also changed quite a bit. We were planning to test using an engine at Valkyria Airport using waste heat from the engine to drive the reaction. But due to delays in getting the engine, this was no longer feasible on our timeline. So we shifted to a lab scale setup in Dr. Blair's lab instead. And that actually improved the final plan because it gives us more control and makes it easier to iterate and collect meaningful data. And that's really where feedback shaped the final plan. Each conversation, whether it was from our advisors or the shop, had us moving towards something more realistic. So instead of just designing for performance, the final design is something that can actually be manufactured, tested, and improved.
Wow, sounds like you had to adapt to real engineering constraints as they came up.
Indeed. We got in contact with Team 2's advisor to see what he thinks about their project.
Oh, look who it is.
Excuse me, you're the advisor of Team 2, right?
You bet, dude.
Could I ask you a quick question?
Sure.
In your opinion, what is the biggest achievement of Team 2's work?
That's a great question. What I think they've done is they have solved the mystery of how to make jet fuel out of ammonia. I've talked to them many times when they've been struggling with exactly what to do. They just have to put a stake in the sand, try things out, and go for their max performance. And they did. It's awesome. Pretty soon we're going to have jet fuel out of ammonia. It's great. It's going to solve all the world's problems.
Right on, dude.
Thanks, man. Press on. Go. Go, team. Go.
He's so cool.
We also interviewed everyday people to see what they think about this project.
So do you think this is one of the first steps towards the future of a sustainable fuel aviation?
Yes.
Do you think the aviation industry should be looking for alternatives to regular jet fuel?
Yes, I think they should. Planes aren't going away, so finding better fuel options makes sense.
Where did we find these people?
I wish I could tell you.
Okay, well, David, close it out for us.
This project demonstrates how we can take ammonia and turn it into a hydrogen-rich fuel source for commercial aviation. We took it from concept to prototype to lab testing, building something we can actually measure and improve. This lays the foundation for scalability and integrating into real-life turbine engines. Every aircraft you see behind me currently operates with conventional jet fuel. This work represents a real step towards cleaner aviation. One day, systems like this could operate in an airport just like this one. Reporting in from...
The future of aviation sure does look promising.
From K&N, I'm Evan McLeod.
I'm Paige Sherrick.
Good afternoon, good evening, and good night.
Okay. Evan messed me up. He was like doing this.
Wait, why would I even say that? It doesn't make any sense. But okay, whatever. Like, why would I just be like, also, I'm being told this project involved a lot of heat, pressure, and engineering.
The hydrogen and nitrogen output is then separated in this gas chromatograph. Chromatograph.
Hey, look who it is.
I am here.
Scooby-Doo, where are you?
I didn't even say anything. I didn't even say anything.
It didn't like.
That was pathetic.